All right, so in this video, I'm going to describe the designing the rope bridge activity we did in class in some more detail so that it's clear what we should learn about torque and rotational statics. So the first thing that we should do is we should draw our image. So here is my bridge here. And we said that this should be a length of 6 meters across. And we have our ropes coming down. They're attached to the very ends of our bridge. And I am going to walk across it, Mr. Z. So, right, here's Mr. Z's bow tie, right? It's not always well tied, so that's why it's a little bit wonky today. And I asked you to design a bridge that would be able to sustain my weight as I walked across it. So we want to find the maximum amount of force that each of these ropes are going to have to hold. So if I remember correctly, I told you that I was a mass of 73 kilograms. So my force of weight, or my force of gravity, is equal to that times 9.8, which gets us 715 newtons. All right, so if I am standing in the middle, or each of the ropes are pulling with even amounts, then we're just going to find the force is half of my weight here, right? There's two strings, there's only one, or two ropes, there's only one of me. So if they're pulling evenly, it's half of each. So the minimum amount of force that is going to be in each of these ropes is 715 divided by 2. Which gets us 357.5 newtons. This satisfies the first part of rotational statics, which is the addition of the forces must be equal to 0. But what about torque if the addition of all the torques is equal to 0? So one of the things that we can do is the origin of our system doesn't have to be one place or the other. It's arbitrary, just like normal. So if I want to find the maximum amount of torque, we would imagine that if one of, well, let me change that around. Let's imagine that one of you is on the left side and one of you is on the right side. As I move towards the right side, the left side is going to get a smaller force of tension, while this side is going to have to push up with more, right? This side is going to feel less weight, less pushing down on them, so they're not going to have to push up with as much. And this side is going to experience more and more force, right? If you're going to keep it up. So just from a quick thought experiment, we can see that the force is not always going to be even, but as I move to the right side, the force on the right side is going to have to increase. Now, mathematically, or in terms of our physics equations, how does this work? Well, we see it happen in terms of the torque. So let's place myself 1 meter from the edge here. So now I am 1 meter away. So this is where the torque comes in, and I am going to try to find the force that the right side holds. And so for simplicity, I am going to make the left side my origin. So this is going to be um, position equals 0. So if my torque is going to cancel out here, then I need to calculate the two kinds of torque, right? My force of gravity is going to be pulling down, and this force of tension is going to be pulling up. And those two forces aren't necessarily equal, but they will have to cancel each other out. So if I'm 1 meter away, that means I'm 5 meters from the left side. So it's going to be my force of weight multiplied by the radius, which is 5. And then I'm going to add it with the force of tension, and it's going to be 6 meters away. So I'm going to solve for the force of tension. So that means it's going to be the negative force of weight times 5 meters equals the force of tension times 6 meters. And then running out of space down here, so I'll just go over to the right. It's going to be the negative force of weight times 5 divided by 6 is equal to my force of tension. Plugging in my numbers, so it should be 715 times 5 divided by 6 gets me a force of weight that is equal to 596 newtons rounded up, and this is negative because we're going in the opposite direction. So I chose the positive direction to be down, up direction is negative. So notice that this is much larger than my equalized force of tension of 357.5, right? I'm almost at 600 newtons. So I keep increasing as I move over to the right. So let's find the extreme case here. Let's place myself all the way over on this side, right? So I am all the way at 6 meters. So now it's going to be my force of weight times 6 plus the force of tension times 6 as well. Well, we see a common unit of 6, so it looks like these two things are going to cancel out. And the force of weight is going to have to equal the force of tension, right? If I solve this out just a little bit, it's going to be the negative force of weight is equal to the force of tension. So the maximum amount of force that both of my ropes are going to have to hold is equal to my weight. So if I want to find that edge case here, if I want to find how much force these ropes are going to have to hold in order to not break, it is going to have to be equal to my weight itself. Because I will be at the left side at one point and the right side at another time. If, of course, the bridge itself, the material that makes up the bridge, is massless. If it had a mass, that would be a different situation. And so we would have to solve for the force of gravity kind of in the middle here, right? If this had some force of weight, and if it was evenly distributed, well, it would be in between both, so the two ropes would be pulling up with the same amount of force. So you just take that force of weight of the bridge itself and divide by 2, and then add it to my weight to find the max amount. All right, so that solves our designing the rope bridge problem from class. Stay tuned for some inertia and torque notes.